Continue what we were talking about yesterday. And so that is quantum numbers. And as always, if you want, more explanations, whatever, I can't see your hands raised, but, if you send me a little note or just, unmute your mic and, say, whoa, whoa, back up or something. So just feel free. At this level, these numbers are going to seem like magic, um, because I'm not really going through all of these, wave equations, etc. But I guess it's just something for this level that you have to just apply. Okay, so we're going to talk about what these numbers are, what they mean, and then we're going to just apply them. Okay.
Broccoli or asparagus, you can let sit for 10 minutes because think about all the different surface area. And if you're washing,
Somebody has to mute. Let's see. Yeah, let's see if that works. Okay, sorry about that. Okay, so we are going to talk about these quantum numbers and the ones that they are. So it's really just a few of them. So we're going to talk about N, L, M sub L, and M sub S. Okay. These next few slides are going to, provide a lot of details about what these are, just to really, really boil it down. N refers to, it's the principal quantum number, and so it's really the size of the orbital. Okay, and it also is like the row of the periodic table. Okay, the L is the shape of the orbital. M sub L is what we call as the multiplicity, or, better yet, how many orbitals there are. And then M sub S is just the spin. And there's only going to be spin up or spin down. Okay, so it can either be just two values, really, M sub S. Okay, so that's really what it boils down to. And then, we're going to look at more details a bit. So the principal quantum number, so N. So it's really the size energy level. This is sometimes called a shell. And so in the Bohr model of the atom, remember where you have, positive nucleus and you've got all these electrons around it. These are the different n's. Okay, so this would be n equals 1, that's n equals 2, etc. Okay. These can only be positive integers. Okay, so you can't have a, -1, and you can't have a 1.4 or something like that. So they are only from 1 to, really, I mean, in theory, infinity, but really, as far as our periodic table is concerned, really like 7 or 8 is really the max of it. And then as the value of n increases, the energy increases, and the average distance of the electron from the nucleus increases. And so that's in this model here. So notice, n equals 1 is very close to the nucleus, and then n equals 3 is getting farther away. Okay, so it is easier to remove an electron from an n equals 3 level than it is to the n equals 1. Okay. All right. The angular momentum quantum number, or L, is again the shape of the orbital. And so really what to remember, so if you write out these possible values, really for our periodic table, this is it as far as all the numbers that L can be. Those correspond to these orbitals. Okay, so if you have an L of 0, that is an s orbital. An s refers to all of these letters actually refer to the lines in line spectra. So we're going to talk about this in a few slides from now. But if you look at the emission profile from different atoms, you can get different peaks. And these letters, or these numbers for the quantum number, the angular momentum quantum number, they refer to what those lines look like. So the sharpest lines refer to S. And then, principal, I guess these were really kind of sharply defined lines as well. And so those are P. Diffuse, so they were a little broader, were D. And then fundamental is F lines. And so just kind of from line spectra, these letters are kind of referred to. And so if you have an L equals 0, that's an S orbital. If it's equal to 1, that's a P. A 2, that's a D orbital. And a 3, that is an F orbital. Okay, and so these really refer to shapes. If we go through shapes, I'm going to kind of show you some better illustrations in a bit. But S orbitals are spherical. Okay, so that's an easy way to remember it too. So S equals spherical. Okay, and so they just are spheres of different sizes. So for instance, the 1s orbital may have a diameter of this. Oops, and you can't see that. There we go. Whereas the 2s orbital would be like that. 3s would be even bigger. Okay, so depending on what the n is, okay, so this is the principal quantum number, the n is the number in front. So depending on that number, you get bigger sized orbitals, okay? So that's your S. The P is a little dumbbell shape, okay? And so again, these are mathematical functions, and so one of them will be a positive lobe, the other is a negative lobe. For this class, it's not so important to really know that. For those of you going on to organic chemistry, you're going to look at overlap of these orbitals and more into molecular orbital theory. We're going to touch just the surface of it, and we're going to see, if two of these come together, they can add, so these overlap in that direction. Or you can have anti-bonding orbitals where it's like this. Okay, whoops. What did I do? No. Whoops. Like that, okay? And so then you have a node, okay, where they don't overlap. In other words, these signs are different. Okay, so we're not going to really get into that hardcore in this class, but kind of file it away for your future chemistries. But they're just really dumbbell shapes. Okay, so a couple of lobes, one being positive, one negative. Okay, and then the d orbitals, there are actually 5 different ones. There are these 3 that are along, or actually in between different axes. And so if we have xy, yz, and let's do xz orbitals, or axes, these have lobes like that. Okay, so they're actually in between these different axes, like that. And again, they're going to have positives and negatives. Okay, so this would be the dxy because it's in between the x and y axes. This is dyz, and this is dxz. Okay, so those are 3 of the 5, and then the other ones are along axes. And so you've got one where it's this. Okay, again, 4 different lobes, but it's actually along these axes. Okay, and this is called dx squared minus y squared. Okay, and then you've got one where it's kind of a weird one. You've got the xy axes, and then imagine this one coming out at you. So the z-axis is coming out of the page, whereas these are on the page. And this has a lobe like that, and then you've got a little kind of a donut shape around it, which is the negative. Okay, so let me show you better illustrations because I'm a horrible artist here. I'll come back to these slides. Here we go. Okay. Okay, so these are the different d axes or orbitals. Okay, what they look like. Okay, so this is d x squared or dxy, I guess, dyz, dxz, dx squared minus y squared, and this is the one with a little donut around it. Okay, where it's all along the z-axis, and then this is what f orbitals look like. So there are 7 of these, and they are a lot more complex. So you've got a lot more lobes. You've got a few of these that are really kind of confusing. So again, more complicated mathematical functions, really. Okay. All right. Okay, so that is the L quantum number. Okay, again, talking about shape. Okay. So any questions so far? Okay, so we've got n is size, L is shape.
Do we need to know the positives and negatives for like the diffuse orbitals?
No, you don't. Yeah. So.
Okay.
Just the shapes. Yeah, and how many like lobes there are. So a typical question on exams, you would be, given what the orbitals look like, and then you'd have to say, is this an S or a P or a D or something like that.
Okay, cool.
Yeah. Okay. All right, so now the magnetic quantum number m sub L. So these will take specific values depending on what L is. And so what's really important is that m sub L can take values all the way from minus L through 0 to positive L. Okay, and again, they're only integers. Okay, so you can't have, fractional or, 1.5s or whatever. Okay, and so in other words, if L is equal to 0, well, I guess it's right there. I was going to ask you, what does m sub L equal? So, yeah, the only value that m sub L could be is 0. Okay, but if L is equal to 1, again, you can have values all the way from minus L, so that's minus 1, 0, or 1. Okay, so in other words, there are 3 different values if L is equal to 1. Okay, and then if L is equal to 2, there are 5 different values. Okay, and one that's not on here, so let's do this one. So if L is equal to 3, then the possible values for m sub L will be minus 3, minus 2, minus 1, 0, 1, 2, and 3. Okay, so in other words, there are 7 values. Okay, and so what's so important about this, you're saying, well, who cares, right? Is that, remember, L refers to the shapes, so the orbitals, right? So L, if it's equal to 0, that's an s orbital. Okay, and from the periodic table, later today, when we start to do electronic configurations, or putting in electrons into orbitals, we're going to see that there's really only one type of s orbital. Okay, so you can only hold a maximum of 2 electrons in any s orbital, whereas an L of 1, okay, this is saying that we've got 3 values for m sub L. Okay, and that is p orbitals. Okay, and so we know that p orbitals can be along each of the axes, right? So we can have, this one, we'll say where that's the x-axis. So this is px, Or we could have this one, which is py. Or I guess we could have, whoops, that's bad. So it's xy, and then let's say z is coming out at us, and we could have it along that. Okay. And so this is pz. Okay, so in other words, you have 3 different types of p orbitals. Okay, and it comes from 3 values for your m sub l. Okay, so really this magnetic quantum number, it sounds really confusing, but all it is telling you how many suborbitals do you have, or how many types of p's, how many types of d's, right? Because above, remember, I drew all these different varieties. So there are 5 d orbitals, right? And so we look in m sub l, there were 5 different values for d orbitals, okay, if l is equal to 2. Okay? And then m sub l for an f orbital, okay, we said that there are 7 different values, so there's 7 f orbitals, okay? All right, so is everybody cool so far? Okay, so n, l, and m sub l. Okay. All right, so far, this is a really good summary slide. So, to kind of, prepare for, not, again, next Tuesday's exam, but the one after that. This is a really good slide. Oh, by the way, too, talking about exams, if this coronavirus scare and social distancing continues till the end of the semester, we will of course not be able to do an ACS standardized final. So I'll just make my own, which I think is probably easier anyway. So I guess stay tuned for what happens with CMU policy. But the way it's going, it's likely that your next exams will all be delivered, even the final, via Blackboard. Okay, so yeah, I guess just stay tuned as stuff develops here. Okay, so anyway, this is the summary of what different values of n that you have. Okay, and then L. I guess, the one thing for L's that is really important, I guess I didn't really talk about that. So the values of L are related on to what values N has. And so L can take values all the way from, you start with 0, but it always will go to N minus 1. Okay, and so if n is equal to 0, L can only take a value of 0, and that means m sub L can only be 0. Okay, and so, whoops, n is not 0. There we go. Sorry about that. N is 1. There we go. Okay, so if n equals 1, and that is the lowest value for n. Okay, you can't have an n of 0. So if n is 1, then L has to be 0. Okay, and then m sub L, remember, is based on what L is too. So these are the only values you can have for your quantum number for an n of 1. Okay, for an n of 2, you have 2 possibilities. So L can be 0 or L can be 1. Okay, and so you will never have an L of 2. Okay, because it always has to be 1 less at its maximum. It has to be 1 less than what n is. Okay. All right, so let's practice with a bit of these. So pull out your cell phones, tablets, whatever you have. I guess your laptops if you're sitting in front of them. And let's do quantum 1 here. Okay, so for which atomic orbital is N 3 and L is 1? Okay. All right, so large majority picking 3p, and yes, you are correct. Yeah, so again, with L's, these are the possible values for L, and those are the orbitals. So if L is equal to 1, then it's p. Yeah. So good, good. Let's look at quantum 2. Okay. This is a good one. Yeah, so which, very, very typical of an exam question, actually. So which of the following sets of quantum numbers is not allowed? And let me show the question here. Right here. Okay. Okay, good. There's a few people, yeah, picking E. But yeah, the majority of you have this one right as well. Yeah. So yeah, B is the correct answer. So for this one, oops. Let me go back to the question here. Okay, so the possible values, so if n is equal to 1, what values are possible for L then? Does anybody? So L starts from what then?
-1.
No, that's M sub L.
0.
Yeah, so 0. Yeah, so L always starts from 0, and then it will go all the way to n minus 1. Okay, but in this case, n is 1, so that's the only one it will have. Okay. All right, and so then M sub L goes from minus L all the way to plus L, but here it's 0, so that's all that you can have. Okay, for an n of 1, you can just have L of 0, M sub L of 0. Okay, and we're going to talk about what this means for those of you who are kind of beyond this already. This, as you know, is the 1s orbital. Okay, and you know that there's only one type of it. Okay, so there's you can only have a maximum of 2 electrons in the 1s shell. Okay, and so we're gonna talk applications here shortly. Okay, so then for the n of 4, what values can L take? So you're starting from 0.
0 to 3.
Yep, exactly. Okay. And then your m sub L, you've got, I guess, different varieties, right? So you've got an m sub L for this one of just 0. For this one, you've got -1, 0, +1. And then you've got, for this one, -2 all the way to +2. And then this one from -3 all the way to +3. Okay. And then this one, it's all the way 0, 1, and 2. Okay. And then all the associated m sub L's. And then this one would be 0 and 1. Okay, and again, all the different m sub L's. Okay, so is everybody cool so far? So, and then, so looking at why this answer's wrong, you know, the n, all the n's make sense, like we don't have an n of 0 or something. And then likewise, the L looks good here, but the m sub L can't be -1. Okay, so for this L, that is. Okay, so the only, what is the only value for m sub L that you would have for this L?
0.
Yeah, so 0. Yeah, yeah, exactly. Okay. So that was quantum 2. Let's do oh, I think this is quantum 4. Yeah, so quantum 3. We didn't talk about m sub s yet. So yeah, we'll come back to this one. So quantum 4. Yep, okay. So this one. So how many orbitals are allowed when L is equal to 2? Okay. Okay, so most people, again, are picking the right answer. So yeah, 5. Okay. And so this is a different way to ask the question. So it's not explicitly saying, you know, what is m sub L? And so kind of realizing that, you know, how many orbitals, that refers to the m sub L value. Okay. All right. And then quantum 5. Okay, yeah, what's a value of L for the orbital shown below? Or beside it, I guess. Okay, yep, so you're getting, yeah, so L of 2 equals a d orbital, and this is a d orbital. Okay, if you have 4 lobes like this, it's a d orbital. Okay. All right, and then let's see, quantum 6, just to get your participation points up here. Yeah, we will come back to this. Okay, so the ones with m sub s. All right, so yeah, we'll come back to these last 2 here. Okay. All right, so I don't know, we've beat this dead horse to death here, but let's, I guess, just do this one last one here. So what do you think? So a 4p, whoops, where's my screen here? There we go. So 4p orbital, what quantum numbers? So n is,
4.
yep, 4, that's the easy one. Okay, then L.
Zero.
So yeah, L, it's a p orbital, so L is 1. Okay. And then M sub L. It's going to go all the way from -1, 0, and 1. Okay. Oops, over here. Oh, what am I doing? Okay, so n is equal to 4, L is 1, and then 3 values for M sub L. Okay. Okay, so something that is, again, not so important for this class, but you will have n minus 1. So depending on your value for n, you're going to have n minus 1 nodes in that. So, these are different types of s orbitals. And so s, remember, they are just spheres. And again, these are mathematical functions showing you the probability of where electrons can reside. And so it's worthwhile noting that, if you have, 1s, 2s, 3s, you can see the diameter of these spheres is going up, as the principal quantum number increases. But you can't have electrons uniformly distributed through all these. So for a 3s, n minus 1 is 2. And so you have 2 nodes. Okay, so there are regions where you have 0 probability of finding an electron. Okay, and then for a 2s, again, you've got 1 node. Okay, so 2 minus 1. And then for 1s, you can find the electron anywhere in that whole diameter. Okay, or cross section. Okay, so it's kind of it is kind of TMI, really, to be honest, for this class, but it's kind of just illustrating that even for spheres there are nodules where you can't find an electron, and this again is predicted by the detailed mathematical functions that these are. Okay. And so these nodes really come from, or I guess an analogy of this is if you tie a rope at one end and then vibrate it, you generate these standing waves. And actually the theory for these orbital shapes, the math behind them, actually comes from this. Okay, so mathematical functions to describe these standing waves. And so this is where we predict, the different kinds of nodes that are present in these orbitals. Okay, so it's really a node just is 0 probability of finding an electron. Okay. All right, so we already talked about, I guess, these shapes, so that's a better illustration of what p orbitals look like. And so we've got this nodule plane. Okay, so really for p orbitals, you have and again, these are kind of emanating from the nucleus, so the nucleus is here. And so for p orbitals, you have a 0 probability of finding electrons near the nucleus, and then the probability goes up away from that, sort of in these, dumbbell shapes. Okay, so when you're over in here, you've got a greater probability of finding an electron than you do right here. Okay. All right. And then these are all, again, different probability functions. But I guess what's uniform is that you have very little chance of finding an electron here, really close to the nucleus. Okay, and this kind of goes with the Bohr model. The Bohr model again, was, this kind of solar system analogy, where everything has these nice orbits. It's really not the same, right? As you see, all these complex shapes. So this is really what the orbitals look like, okay? But he did have it right that, the electrons are, away from the nucleus. You don't have electrons right on top of these, okay? So 0 probability of having an electron here, but then here, now you do have electrons, okay? All right. Okay, so the line spectra, so this is what really those orbitals, what those letters really refer to, are the line spectra. And so if you are to look at an excited different atoms, and so for instance, if I apply an electric current through glass that's filled with sodium, for instance, you'll see, I guess just a few lines here, but you'll see some yellow lines around, what is that, 580 nanometers, okay? So some closely spaced lines, okay, versus hydrogen, you have 3 different lines. And these different lines, they refer to when you're supplying energy. If I just use this Bohr model as an example, if I hit it with a certain amount of energy, okay, so remember, energy is h nu. So if I hit this with energy, what you're doing is you are promoting electrons from different orbits. So let's say from this one, I now have promoted it to this orbit, okay? And so when it does that, it is absorbing a certain amount of energy here, okay? And so all of these different lines correspond to moving electrons between all these different orbits. So maybe one to here, there to there, there to here, okay? And so depending on how much energy is being absorbed, you're getting all these different absorptions, okay, and electronic transitions. And so we can do a calculation of how much energy is required for that, using this equation. It's not something that I focus on really, so I'm not going to put questions on an exam for this, but you can do the calculation to calculate, what wavelength this transition would be. For instance, if you're going to go from the n equals 1 level to the n equals 4 level, you can do the calculation of how much energy does it take for that to happen. Okay, so again, it's not something I'm going to ask, but you can actually calculate all of these that way. Okay, so you can actually do a pretty good job actually of calculating the theoretical line spectra and then compare it to the actual one. Okay. Whoops. Okay, and so these are the transitions. This is kind of the Bohr model view of it. Okay, versus, and this is shown, I guess, relaxing and then emitting radiation. And so there's 2 ways. So as I was talking, you can promote an electron, let's say from this energy level to this one. Okay, and that takes energy. Or you can relax from this one, from this top one down to the bottom one, and that will emit a certain amount of energy. Okay, so these are shown, in the other way. So all these are being relaxed, and so those correspond to emitting a certain characteristic frequency of radiation. Okay, so again, you can just do calculations here. All right, so the last quantum number, so kind of where we're going to end today, is this m sub s quantum number. So this is the spin quantum number. And so this is really related to electrons having a spin. which results in a tiny, it's very, very tiny magnetic field. And so we will always talk about it either being spin up or spin down, okay? And what's most important, without getting really into details about, why and how, etc., is this principle. And so we're going to use this a lot at our next class, I guess next Monday, the Pauli exclusion principle. So when we start to put electrons in individual orbitals, this is saying that no two electrons in an atom can have the same set of 4 quantum numbers. And so let's look at what that will look like. And so let's look at the 1s orbital. Okay. And so I'll just write a little box, okay, that shows this 1s orbital. What are the 3 quantum numbers? So, n, L, and m sub L for a 1s orbital. So what is n?
0.
Yeah. Or no, n. Yeah, n can only start from
Oh, right,
1.
it's 1.
Yeah, and then it's also here. Yeah. So you have n is 1, and then L, I think that's what you wanted
0.
to say, is 0. Yeah.
Good.
And then m sub L, the only thing it can be is 0. Okay. And so the Pauli exclusion principle says that no two electrons can have the same set of 4 quantum numbers. And so this is where we put together m sub s. And the only values that m sub s can take is either plus 1/2 or minus 1/2. Okay. And those are really illustrated by this. So this corresponds to an m sub s of plus 1/2. Okay, so I'll call it spin up. Okay. And so what Pauli exclusion principle is saying is that you cannot have this as your electronic configuration. Okay, because these 2 electrons would have all 4 quantum numbers would be the same, right? So this one would be plus 1/2 and this other one would be plus 1/2. Okay, so really to put 2 electrons in the 1s orbital, you have one that's spin up, the other one has to be spin down. Okay, so this is the Pauli exclusion principle. Okay, so this is m sub s equals plus 1/2, m sub s equals minus 1/2. Okay, so everything else, so this, for instance, has the same n, l, and m sub l. They all, both of these electrons do. So we can't have their spins the same. Okay? So does that make sense so far? Okay, hopefully it does. Okay. All right. I think that is actually a good place to stop today. And then tomorrow, or I guess not tomorrow, next lecture, so I guess that will be next Monday. I'll start off taking your questions about the midterm since it is going to be next Tuesday. So we'll, again, look at the video. I posted the video of me working out all the questions. So hopefully that should address all of those questions. But if you have any other questions or other review you want me to cover on Monday, I can do that. And then we'll go on to using these 4 quantum numbers now to fill in what we call electronic configurations. And so, looking at the periodic table, for instance, lithium has 3 electrons. What orbitals are those going in, and are they spin up, spin down? How do we place them in there? Okay, so we'll get into that next Monday. All right, so again, stay safe, stay indoors, maybe have some green beer or green Kool-Aid, whatever you want at your own house. But yeah, I will see you next week. Okay, take care.